Okay, welcome to the UEI Technical Masterclass. I hope everyone's doing well today and weathering this current pandemic. I'm Bob Finn with UEI, and today's webinar is entitled ARINC429, Message Handling and Application Development. This is the second webinar in our month-long focus on avionics. In today's webinar, we'll be exploring the ARINC429 protocol and UEI's 429 capable I/O boards. This is not only a presentation of technical information, but an opportunity for you to interact with our application engineering team. Just fire off any questions you have using the webinar chat tool, and please don't be shy. And so, without further ado, I'm going to turn it over to today's presenter, Austin Turner.
Thank you. So as Bob mentioned, my name is Austin Turner, and I'm an application engineer here at UEI. For those familiar with our masterclasses, welcome back. And for those new to our masterclasses, welcome. I hope everybody enjoys the class, learns something new, or at the very least, gets some of those creative engineering juices flowing. So for today's masterclass, we're covering an avionics protocol, ARINC429. Let's jump into the first video to get a background of what is ARINC429.
Hi, I'm Phil. I'm an application engineer here at United Electronic Industries. An aircraft has many systems: guidance, navigation, altitude, flight management computers. All these systems have to work together to accomplish a successful flight. ARINC429 was designed in the 1970s to accomplish this goal. It's based on labels with equipment IDs. Labels help identify the intent of the message: gain altitude, turn, give me information. The ARINC429 standard gives guidance so different manufacturers can have the same type of equipment giving the same type of labels. There are a limited set of labels, so label 409 on a GPS may have a different meaning than label 409 on an altimeter. This is possible because the 429 standard also allows for an equipment ID field, so you can correctly interpret 409 for different pieces of equipment. UEI supplies many different application examples for each of our I/O boards. This example is for the 429. It's a C-based example, and basically what I've done is gone in and set the IP address, set the location of the I/O board, and I'm going to run the sample. It is sending data out one channel and receiving it on another through a loopback adapter. As you can see here, there's different labels being sent, different data sets per label, and this particular entry just cycles through a bunch of labels. So here's a LabVIEW application that we wrote and supply in our install. So you can see the LabVIEW codes here, and we can simply start the application and send data. Again, out one channel of our card into another channel of our 429 card. We can change the label, we can change the data, and exercise the system. Your particular application may need to continually send and receive. That's fine too. So this example allows you to manually send data. You could also set the system up to automatically send data, either through a FIFO or an advanced scheduler, which we've created. Please look for our other video on YouTube that will detail out the FIFO and the scheduler. ARINC429 is supported out of the box and ready to go on many different UEI form factors: UEI Net, UEI Cubes, racks, flat racks, mill cubes. These all operate in either tethered mode or untethered mode. Tethered mode requires a computer to be running the program, and untethered mode is a truly autonomous embedded device capable of recording or communicating ARINC429. Our systems are programmable in C, C++, through LabVIEW, MATLAB, Simulink. You have a wide variety of choices to accomplish your application requirements. And like all our products, our ARINC429 card meets the demands of a variety of rugged testing conditions, including the ability to withstand 100G shock, 5G vibration, temperatures ranging from -40 to +70 Celsius, and altitudes up to 70,000 feet. Got a question about this product or any of our other hardware and I/O? Visit our website, send us an email, or give us a call. Our support staff is ready to help you.
So that video covered some of the basics of ARINC429, but what is ARINC? So ARINC stands for Aeronautical Radio Incorporated. It was a provider for avionics protocols, systems, and the like. So it's now part of Rockwell Collins, which I guess actually now is Collins Aerospace. ARINC429, you'll sometimes hear it referred to as Mark 33 DITS, and that stands for Digital Information Transfer System. So what is the protocol? So we have two main rates that we use. It's either going to be 12.5 kilobits per second or 100 kilobits per second. It's unidirectional or simplex communication, meaning information travels in only one direction on the bus. You can have multiple buses, so that way you can have communication in both directions, but again, that's on different buses, so it's still going to be a unidirectional bus. I'll be saying this a lot in this presentation, but the content of the message is really determined by looking at the label. So the label is going to help us identify what is this data representing. And it could be heading, it could be airspeed or other information. And then the data, we'll have 19 bits of data. All those bits could be used, but we'll take a deeper look into the ARINC429 word in the next slide. It's a low latency protocol and it's proven. But with that low latency, you also have things like no error correction, and you have lots of wiring for that unidirectional bus. So when you have lots of wiring, you're going to have lots of copper, heavier planes. So you'll see nowadays a mix of ARINC429, but you'll also see it mixed with MIL standard 1553 and ARINC664, which is AFDX, avionics full duplex switched Ethernet. So let's take a look at the ARINC429 word. I like to know exactly what is going on the bus when I'm looking at a protocol. So lower in the screen, you can see the ARINC429 word format, and we'll go from left to right. So we have the parity bit, and that's typically odd, but some devices can use even parity. Next, we have the SSM, which stands for Signed Status Matrix. And depending on how the data is encoded, that signed status matrix, the SSM, can indicate direction, operating status, or yes, even the sign of the data, as the name hints towards. Next, we have the 19 bits of data, and the next slide we'll take a deep look into what the data could be representing and how it's encoded. Next up, now we're over to bit 10 and 9. We have the SDI, or the Source Destination Identifier. Now SDI is optional, but when used, it can identify the source of the transmitter, or it can direct which nodes should listen to that word. For example, if both bits are all set to 0, this means that all receivers should listen for that message. Now the label is typically 8 bits. Since SDI is optional, some devices use SDI or even some data bits for label and equipment identification. But we'll focus just on the 8-bit representation showed below. So although ARINC words are sent LSB first, the label itself is sent with the most significant bit first. And so we can see the MSB is sent here first. And that's to keep compatibility with legacy systems. Since it's an 8-bit value, it's often represented in octal format. So you want to be aware whether your device is using base 10 hex, or octal. So here's a breakdown of the data field. So again, data is represented with 19 bits. We may use all of those bits or just some of them, depends on the device. So the encoding can be one of these four options. So we're gonna have BNR, binary number representation, and this is typically 2's complement binary value. So since we don't use the full 19 bits, or we don't have to use the full 19 bits, you need to consult with your device manual to determine the bit length and also the resolution to determine the true data value. With BNR, we can still represent floating point values by setting a specific range so that each bit represents a typical 2 to the power value. For example, if we're trying to represent 128, that's the full scale value, and we use 9 bits, then we know that each value can be equivalent to 0.5 units, or the LSB would be equivalent to 0.5 units. Next up, we have BCD, binary coded decimal, which is not specific to ARINC429, but in the ARINC429 protocol, we can encode the data using 4 bits to represent each decimal digit, which again, we need to incorporate a device-specified resolution and bit length to translate to actual value. Next up, we have the raw values, and this is going to be used for digital states, on-off states. So we're looking at a single bit or several bits to know different digital states. And finally, much less common for ARINC429, we have ASCII format. So again, I want to reiterate that ARINC429 is based on messages with labels, and this label identifies the content of the message. So as mentioned in the video, this could be altitude, this could be distance to go, it could be temperature, such as fan inlet temperature. The standard does provide a set of labels to be used by manufacturers, so there is some consistency, but not all manufacturers follow that standard. So one of the most consistent labels that we've seen is distance to go is typically label 1. So UEI and ARINC429. So currently we have 3 different boards. I've labeled them here. There's a mix of different TX and RX. The last one on the list, we have 16 channels that you can configure between TX and RX. And there's also a dedicated 8 receivers. All the boards support the 2 different baud rates, so 12.5 kilobits per second or kilohertz and 100 kilohertz rates. We also support custom rates. So we're flexible there. We've had some customers that needed 14.5 kilobits per second, so our boards can support that as well. And then some features we'll take a look at are label filtering, our TX or transmit scheduler, and more. So since I've mentioned, ARINC429 messages are based on labels only about, 3 or 4 times so far, let's talk about filtering those messages. Your ARINC bus may have many labels, sometimes well into the hundreds of labels. At times, you're only interested in a few labels, or possibly you only want to view the data if it's new. So our ARINC boards support a filter functionality where you can program in these various labels, maybe set a flag for new data only, and now your software application won't be overloaded with data, and you can hone in on the label of interest. So a quick diagram below, just very rudimentary. We have a label filter for octal 7.4, and we can see that the label of 7.4 does come out to our user application. So how about the transmit side? So I'm gonna show another video that goes into details about the transmit, but let's get an overview here. We have 2 basic methods. We have FIFO-based sending, which is putting ARINC words into a hardware-based FIFO on the UEI board. This could be a single word, it could be multiple words. And also this could be paced by a hardware clock, which determines how fast to empty the FIFO in case you want to spread those messages out by a specific time period. Or it can be paced by your application and will empty the FIFO as fast as possible. We also have a scheduler-based transmit function. One of the common methods of ARINC429 is to send out data words at periodic intervals, so that if there was an issue in message transmission, because again, we don't have error correction within the protocol itself, there wouldn't be a significant delta of data that has gone missing. So there's minimal consequence of that error in message. So the UEI scheduler allows your application to simply program a set of labels and data and send them out at specific rates. Also note that adding in the filter functionality, we can set a specific label that when received through that filter will trigger one of our scheduler entries to begin sending. And so now we'll take a quick break, go through some Q&A, and just kind of thinking about what are your ARINC429 requirements. If we don't get to your question today, or maybe you have a question at a later time, then we want to hear from you. We want you to contact us about what do you need with your ARINC429 system. So let's go through the questions. Let's see what's coming in. First question is, can I control parity of the transmitter? How about the receiver? So for the transmitter, yes. Specifically our ARINC429 516 board, you can set that transmitter to be even parity, odd parity, or space parity. And when you set the parity to space, basically that gives your application complete control over parity. So there's not going to be an automatic calculation of the parity bit. It's going to listen to whatever you've programmed it to be. So whether you want it to be 0 or 1, it doesn't matter, the number of bits that have been in the message. On the receive side, you can program the parity into the filter, but we're not going to set the parity in the receive side, of course. Another question, can I use a scheduler on one channel and FIFO-based sending on a different channel? Yes. So each channel can be configured in its own rate. So you can have one channel that's using 12.5 kilobits per second and 100 kilobits per second, but also you can configure one channel to be sending with a scheduler and another channel to be sending by that simple FIFO-based sending. Can I use different channels at different rates? Yes, I think I just answered that. So you can have different channels running at the different rates. You can also set to a custom rate if you need that. Can you schedule multiple labels to go at the same time, such as latitude, longitude, course, fine? It depends on what you mean by same time. You can have the same delay, but they won't necessarily be sent out at the exact same time just due to, you're sending a message out on a physical bus. So it would be one after another. You could use two separate channels, but you have to be careful because, multiple transmitters on the same bus, if you have collisions. So I would say not necessarily at the exact same time, but we'll look at a LabVIEW example later where we can program the same exact delay for both those labels. So they will be sent out consecutively at that time period. Can I use this board in a cube? Yes. So all of our boards can be used in any form factor that we offer. So although this demonstration, there was a diagram or a picture of a DNR board or rectangle board, all of our boards are worked throughout any of the form factors. It's also worth noting, though, that you can't take a DNR board and plug it into a cube, which is a DNA board. There's a slight difference between the form factor of how they plug into the backplane, and that's the only difference between the hardware. So if you're developing software and you're writing it for a normal rectangle, and then later you want to go to a military chassis, software will be identical. So that board can be used in all the various form factors. Let's see. Can you please give an example of coding floating point value in a message? I think we should take that one, let's try to answer that outside of here, because what we need to do is we need to look at how many bits we want to represent that floating point value with, and then put that into the ARINC429 word. So again, the way that we can represent the floating point value would be to set a max value that is less than the amount of bits that we use. So if we are going to use the full 2 to the 19th of those bits, and we set the value to only a max of 128, then automatically our resolution is higher than the value of our max value. Can you please elaborate on non-tethering mode of operation from programming perspective? Yes, so we have two modes of operation, or two main modes of operation. One we call tethered or powered DNA. So that's where your application runs on a host PC. And your application could be written in C, C++, LabVIEW, MATLAB. I know I'm missing a few of those, but there's a lot of languages that we support. So again, your application is running on your host PC, and it's communicating over Ethernet to one of our chassis. In the embedded mode, this is where you are cross-compiling your application to run directly on our hardware. So if you use the C API, it's going to be completely identical whether you use it in the Powered DNA mode or the embedded mode, which we call our UEI pack. So hopefully that answers your question. If not, we will have a masterclass at a later time talking about our UEI pack. And I think that information could really help elaborate on the differences between Powered DNA and UEI pack and what's powerful about using the UEI pack. Are there any programming languages that are not supported? There certainly are going to be programming languages that are not supported. I couldn't list them here, but we do have new support coming out within our next release for Python, which is a very popular programming language. So we've incorporated that into our next release, Python 3.8 support. Are there Simulink blocks for ARINC? Yes. And maybe this warrants another masterclass for our UEI sim. So we have Simulink blocks that you can use to create your application within Simulink that you then cross-compile and run it on our UEI sim hardware. So it's an embedded process. We can also share that data and see the data coming through in the Simulink application. If you would like a UEI sim masterclass, please let us know. We definitely would love to get your guys' input on what masterclasses you want to see next. Okay, so I'm going to jump into the next video, and then I'll continue with the Q&A and also show the example.
Hi, I'm Phil, an application engineer here at United Electronic Industries. As we detailed in our last video, ARINC429 is the standard for commercial and transport aircraft. In this video, we'll discuss the specifics of ARINC429 message transmission and the unique technology UEI has brought to the table to help you accomplish your real-world application goals. Typically, ARINC429 allows for two standard transmission rates, one at 12.5 kilohertz and the other at 100 kilohertz. Based on customer requirements, UEI has added the ability for you to adjust the transmission rates. You can increase each standard rate by 33% or decrease each standard rate by 33%. Next, we'll discuss how to send messages. There are basically two methods, either through a FIFO or using our advanced scheduler. And you can actually use a combination of both. FIFOs are commonly used in software to send messages in a particular order. The UEI-429 I/O board provides you with a 256-word output FIFO. There are actually two modes to the FIFO: paste and non-paste. Paste allows you to control the intermessage timing by using a user-defined clock. Without paste mode, your application simply controls the timing of the transmission. In computing, scheduling is used to coordinate work by using resources other than your application program. The UEI-429 scheduler includes a table that allows up to 256 labels per channel. This scheduler can be started by your application or automatically based on the receipt of a specific label. The UEI scheduler allows you to send multiple messages at different rates per message. It also allows for many real-world scenarios, such as having one or more entries depend upon another entry being transmitted. In other words, a master-slave functionality. Allowing a time delay, such as a countdown of how many scheduler iterations to wait until this particular message is sent. The ability to specify that a message is only to be sent once and never again. The ability to receive a notification that the message was sent so you can update the message if you wish. Let's talk about the FIFO and the scheduler interacting with each other. By default, the FIFO runs at a lower priority than the scheduler. This means that it will only output data when the scheduler is not sending any data. If you're not using the scheduler, the FIFO is the highest priority object in the system, and thus will always be sending messages. The scheduler and FIFO priorities may be interchanged simply by setting one bit in a register. So if you need to interrupt and usurp the scheduler, you can actually make the FIFO the highest priority in the system, have it send X number of commands, and then change it back to have a lower priority than the scheduler and resume. Got a question about this product or any of our other hardware and I/O? Visit our website, send us an email, or give us a call. Our support staff is ready to help you.
So let's jump into the example, and then we'll go back to Q&A, because I see at least a few questions have come in, and I'll make sure to get to that before we wrap up here. So here I have Powerdine Explorer, and that's just used as a quick view of what boards do I have in this chassis. So here I have the ARINC429 516, and right from Powerdine Explorer, I can configure those channels as RX, as TX. I could add a scheduler, and then I could monitor the data. Similar with the 566, this has 6 transmit and 6 receive. We can't configure the TX and RX; those are 6, individual channels. But we can look at, we can change the speed, we can change SDI, and we can change the parity. Also from Powerdine Explorer, we can get a wiring diagram. I know this text might be small on some screens, but the main idea here is we can quickly view how to wire up the 566 so we can see the A and the B lines of the ARINC429 signal and how that's routed out of the board. So let's jump into the LabVIEW example. First, let's go to a simple example of writing and reading from an ARINC429 port. So I'm not going to go over too much of the technical details of resource strings, but basically here I'm talking to device 0. We'll change this to import port 1, and the output is 0. And I have one of our loopback adapters connected, so it connects those 2 channels. So when I run this, I can send the data, and I can see that it's being received. Now, one of the functions of the 429.516 is we can run loopback testing without anything connected. So even if I was to take off that self-test adapter, we can have the output and the input on the same channel. Oops, I have to run the LabVIEW example. And we can send and we can see the data coming through. So that's a simple example. That is using the FIFO, but it's only sending, how much I tell it to send and when I tell it to send. So let's look at an example of using the scheduler. So we'll take the 566. I've wired up the output of channel 0 to the input of channel 1. I have multiple words set on my scheduler. And now if I run it, I'll see those words coming through. And if we took a look at this, these are hex values and these are decimal values. So we can see 181 CD would correlate to decimal 98765. We can also enable the filter. So let me do that. And now we only see label 10 or hex A coming through while all other labels on the bus are currently ignored. So let's take a quick look at the block diagram here. So for those familiar with LabVIEW, we see some of our polymorphic VIs. So we can use this drop-down menu to change between the different subsystems that we use. Here we have ARINC429 input and output. We're using our messaging IO. We're configuring our scheduler. And then depending on this push button here, we're gonna either use a filter or disable the filter. Once we start, we'll start reading those ARINC words and we'll parse out the label data, SDI, SSM, and parity components of that word. And that's it for the demo. So now I'll go back to questions. If you have any questions on this demo, any other question about ARINC429, feel free to send those in. So let's see. In a cube system, the data timestamp synchronized with other analog input channels in the cube? So it can be. What we can do is we can route the same clock to each timestamp of each board. In a previous masterclass, we talked about where does that timestamp counter or the clock that we're using for the timestamp counter come from. We can synchronize it to a PTP or a 1 pulse per second in the case of using a GPS as the main source of time. Can the scheduler table be changed as it is running? That's a great question. I actually don't know the answer. Brian, if you know the answer, chime in. Otherwise, we'll take that one down and we'll check out to see if the scheduler table can be changed as it's running.
Yes, my name is Brian Dow. I'm also an application engineer with UEI. Yes, so the answer to that question is yes. You can, the scheduler is running, and if you want to change, a single label in that scheduler table, you can do that while on the fly while it's running.
Thank you, Brian. All right, let's see what other questions. Can I take 429 data and send it out over 1553 and vice versa? Yes, you can definitely do this. So you can use this as basically a protocol exchanger. Since we support 1553, 429, various other serial protocols, avionics protocols, you can receive data on one board and send data out on another. It's up to your application to convert those. But again, that's definitely possible. Can I transmit the data from a standalone unit to LabVIEW? Yes. So I think we should dive into this deeper in our UEI PAC masterclass. We have methods to send data out from our embedded controller. So that could be UDP, it could be TCP, and we also have a specific package that's called our UEI PAC HMI, or Human Machine Interface. And what that does is it creates a sort of shared data variable so that you can share the data from a UEI PAC to a remote application. And certainly that application could be LabVIEW, it could be Python, it could be just about any language in that case. How can I self-test an ARINC429 I/O board? So one of the features we do have is that loopback test that I discussed, in that we can run the board without anything connected and read on the same channel that we're using for output and input. Hopefully that makes sense. So channel 0 can be used for input and output. So you can send a message and receive it without anything connected. We also have self-test adapters that basically for the ARINC boards will take transmit channels and connect them to receive channels. So you can set up an application where you're sending all this data, and then those channels can receive the data that you're sending. Is there a quick way to do an incoming test to test the board? Yeah, so you can write an application. So you can use LabVIEW, you can use MATLAB, or all those various programming languages that we've discussed that we support. But also you can use Powerdine Explorer. So with the ARINC429 boards, you don't get every single feature. The label we don't have included into Powerdine Explorer, but you do get the scheduler, you do get the FIFO rights. So we can transmit data using Powerdine Explorer, and we can monitor the data. So that can be used as a quick test without having to write any software. We've written that application for you for that quick test capability. A question was, okay, 1553 and 429, but how about analog and digital I/O? Again, it's all the I/O boards that we support. It's not just 429 or 1553, synchronous serial, asynchronous serial. We support analog inputs, outputs, and digital I/O as well. So your 429 message may come in and it may say a temperature is out of range. And then you can change an analog output or change a digital output, or maybe your digital input is reading something and that triggers you to send an ARINC429 message. All of that can be incorporated into your application. And again, we support those various protocols along with your more general purpose analog and digital I/O. All right, I'll do a last call for questions. I don't see any more coming in. So I want to say thank you for attending this masterclass. I hope you enjoyed it. Again, I definitely enjoyed being a part of presenting this.
You all set, Austin?
All set, Bob. You can take back over.
Well, I want to thank you, Austin, for doing this today. And thanks to everyone for participating in today's webinar. Looking forward, we'll be continuing our masterclass series at the same time next Thursday. May is avionics month, so we'll be focusing our next two on MIL Standard 1553. And coming up in June, we'll be presenting on the UEI Programmable Automation Controller Platform. We'll have a look at OPC and Modbus and a presentation on LabVIEW. Additionally, we'll record every webinar and post the video online the same day. You can also watch any of our previous sessions either on our YouTube page or on our webpage, ueidaq.com/videos. And finally, we'll be contacting anyone with unanswered or partially answered questions. If you have any additional support needs or you've got suggestions for future webinar topics, please email us at support@ueidaq.com or give us a call at 508-921-4600. And thank you again for joining us. We hope you found this webinar useful. We hope to see you again next week. And as always, until then, please, please stay healthy.